and to tell you something about interactions of negative ions with ultracold atoms. Think about the universe. The universe is neutral overall. We've heard many talks, many great talks about cations. Now we actually switch sign because there are also, not as many cations out there as there are anions as there are cations, because there are free electrons, but many electrons actually also get caught up. And we're interested in the dynamics and the reactivity of negative ion species in Innsbruck. And today I will focus on recent work that we did with together with Matthias Weidemüller and his group at the University of Heidelberg on interactions with cold atoms. But before, just one slide to motivate a little bit of the different things that we have been doing and that we're interested in. That is to look at state-dependent, quantum state-dependent rate coefficients to understand, quantum state-changing processes in collisions, like here in this case with one of our guinea pig molecules, OH-, that you will see more of later. We're also interested, as we heard already from Heather, on interstellar ions. Again, here we focus on the negative species, and there are quite a few out there, and we want to understand their properties. We're interested in spectroscopy, like, for example, in rotational spectroscopy in the terahertz domain, here for a negative ion deprotonated ammonia, NH2-, which has not been found yet in space, but could be given these frequencies. And also recently on dipole bound states. And I will show you a dipole bound state also in the course of this talk. Because for all of this, we're interested in getting cold, but with negative ions, we resort to buffer gas cooling with the buffer gas that is available, which is helium. And so we're essentially limited to 4 Kelvin, give or take maybe 10, 20, 30% or so. If you're really brave, you can maybe devise one of these buffer gas cooled traps also with the 1 Kelvin cryostat, but it's not done yet. And so with negative ions, when it's really stuck with this helium boundary, and the question was, can we get colder? And I should say we rely on buffer gas cooling in radio frequency traps that have been pioneered by Dieter Gerlich, who passed away 1.5 years ago. And I'll show you how these kind of multiple traps also have been coming along and what kind of new technologies we have developed for this. And so the outline of my talk is I want to first show you wire-based radio frequency traps that have been important for this work and also are useful for other work. And then discuss collisions of negative ions with ultracold atoms, and then show you a nice, interesting system that has the potential to be laser cooled in the future. Let's start with the system. So the idea is very simple. The putting it into action then turned out to be a long story. The idea is simple. Take a different buffer gas, say ultracold gases that can be laser cooled. Rubidium was the simplest species we had available, and that in principle should also be possible for negative ions then. So overlap a rubidium cloud with an ion trap. We want an ion trap that is sort of accessible for Mott beams, and we resort to multiple wire traps, multiple traps in the first place, because they reduce the micromotion in the center of the trap, and that should be advantageous for cooling. When we go for an octopole, the effective potential scales as r to the 6 instead of the r squared dependence in the Paul trap. And the first wire trap was actually built by Johannes, who's here in the audience, when he was still a postdoc in Freiburg. And it's this one, motivated by high energy physics, who use wires for building detectors that are very transparent. We got these wires and stretched them out and got this trap with 8 wires soldered to printed circuit boards with a very well-defined tension, so that in the center of this we could trap ions and, for example, also put a magneto-optical trap in between. This is an old photograph from more than 10 years ago with a dispenser-loaded mod. These wire traps actually are different from the usual traps that we've been using in the past, pioneered by, as I said, Dieter Gerlich, because these traps used to approximate the hyperbolic field that you ideally want for a perfect multipole, shown here for an octopole in blue, by circular cylindrical rods of the appropriate radius. And so instead we use cylindrical wires, which are way smaller than this. And that essentially, seemingly creates a big problem, which turns out to be not such a big problem after all. And that is that the potential, the effective trapping potential, becomes phi dependent. So becomes dependent on the azimuthal angle, as shown here. This is the potential, the effective potential in such a trap at various locations along the radius. So large radii to smaller radii. And you can see at substantial radius out here, there is a strong modulation, and that can create problems. However, as soon as one goes inward, these drop very rapidly. And in fact, in the area where the classical turnaround radius would be of a thermal ion at, in the Kelvin range, it no longer becomes a problem. And these wires actually can produce a fairly, phi independent effective trapping potential in the center. And we also did various simulations within these traps to show you, for example, this is the energy distribution in these traps. And they actually, for ions trapped, they don't depend on the type of trap. So ions really are, confined enough in the center of these traps to no longer care whether these wires actually, follow the hyperbolic rods or not. These distributions, they can be fitted with thermal distribution, which is the green curve here. But actually, when you go and look more carefully, then you see deviations at high energies here. So there's a logarithmic scale here, and this is roughly a room temperature ion ensemble. And you can see there are actually small deviations, and we can nicely model those with the Thales distribution, which takes in particular into account that there are these high energy tails here. And so this tells us we that we understand the ion distribution, given the fact that buffer gas cooling in the radio frequency field, even though the octopole has less of that close to the ion center, ion trap center, does play a role and heats up the ions to some degree. But of course, this is a small fraction of the ions, much smaller than you would have in a Paul trap. So this technique, actually, we liked it so much that we decommissioned our classic 22-pole trap and also now have 2 of these 16-pole wire traps. And one of the reasons is that we were able to use now copper wires also instead of the molybdenum wires we had in the past, because in this way we can make these traps cryogenic. And here you see a design that we recently published, and made out of in a copper container. We can put 16 copper wires and produce an effective trapping potential, in this case proportional to the R to the 14, so very flat in the center, with a minimal amount of material, which actually turns out to be very advantageous. Here you see a photograph of this trap. You can see how transparent it is from the side, so you can do various applications in spectroscopy with this device. And the rods are 10 times thinner than previously. We have this very good optical access, and we actually reach, with proper shielding, 3 Kelvin on our new cryostat with this. What's actually nice and very beneficial for cooling ions is that there is less surface area in the vicinity, because surfaces are the areas that you have poor control over. They can be dirty, they can create pet potentials, and the surfaces are further away, and they also show less surface area towards the ions. The essential only caveat is that we need a higher radio frequency amplitude in order to get the same effective potential. That's a technicality. But besides this, I don't show this here, but we were actually able to see that this trap cools better in helium buffer gas than our previous ion trap. And also here I have another picture of this showing that the effective potential depends now on the phi angle. This is a different direction. A different way to visualize this as a function of radius. You can see the R to the 14 increase of the potential here, and it scales. It has a higher prefactor. It's the R to the 14 is here, and it actually increases more than that in the direction of a wire, and less than that between 2 wires. But on average, and at typical turnaround radii somewhere here, the potential still looks the same for trapped ions. And you can see the same here in this contour map of the effective potential. So it's a nice and versatile tool for various things. for example, for these collisions with ultracold atoms. And so for this, we are using a hybrid trap together with a magneto-optical trap, which we improved for the purpose of this work. Let me just show you. We have a pulsed ion source. We want to make negative ions, so we don't do that by photoionization, obviously. So we have a little plasma discharge across a supersonic jet, and then the ions are mass selected. This has to be done in a separate chamber to avoid perturbations of the trap. Nevertheless, we still see some bit of a gas increase here when the ions are produced. Ions are then transferred towards the magneto-optical trap into the trap, which you can see here. Here's our wire trap, the mod in the center. And then down here, we have the extraction path towards our ion detector, where also we use time of flight, no fancy high resolution, but just a simple time of flight distance to count the ions and distinguish them. So the first experiment we already did many years ago with the previous mod, and which directly showed the essential problem that once we put the mod in place, we actually have a significant loss, and that is that we have to deal with this kind of reaction here, which is one of the processes we then had to understand in more detail. And you can see OH minus can also actually react chemically with rubidium and produce an RBOH neutral and a free electron, a process called associative electron detachment. In order to improve that and to understand where this is coming from, we've devised, we've installed sort of two technical improvements. One is we load more atoms from a two-dimensional magneto-optical trap, and also have more stable loading conditions. And the other, more important even, is that we use a so-called dark spot, and that is that we image sort of a shadow into the magneto-optical trap for the repumper, so that the atoms are actually trapped in a non-fluorescent state in the magneto-optical trap, and we can make the atomic cloud dark of purely ground state atoms, because we want to distinguish whether the ground state or the excited state of the atoms is actually contributing to the losses. And there were lots of debates theoretically whether there is a curve crossing or not. I'll show you the outcome. But our hope was at least that we would not have losses with the ground state rubidium atoms, and that would then help us to do cooling. And so the improvement you can see nicely visualized here. This is now density measurements using absorption imaging, and you can see how the particle density, the atom density here increases, and we reach more than 10 to the 11 particles with more than 10 per cubic centimeter with more than 10 to the 9 particles in the trap. And we can control the bright state fraction by putting in the repumping and possible depumping light where we want it, so that we can control what fraction of these atoms is in the mod cycling transition, so always oscillating between, or scattering light between the 5s and the 5p states, and how much is actually hidden in a non-fluorescent ground state. And with this, we overlap now ions and atoms again. In fact, we also want to measure absolute rate coefficients here, and it was mentioned that you need to know your overlaps well. And for this, we have another technicality here, which is this photodetachment laser beam, a position tunable laser beam that can neutralize the negative ions and create a map of the negative ions, so that we then know where are our ions, where is our magneto-optical trap. We know this from the absorption imaging. We have to overlap them, and then we can create a very accurate profile of also of the overlap function. And so this, for example, is a probability density distribution of the ions, and you can see this is the ion. The black points are the measured data of the ion density distribution along the trap. This is the trap center here, and we can compare this again with simulations. And again, you can see that the thermal and the Thales can be used here. Here we cannot distinguish between the two, but what we can do is we can get a temperature, a translational temperature out also from this, because in the effective potential, the higher the temperature, the more the ions will be spread out in this distribution. Okay, and then we did the experiment with different bright state fractions, and you can see, well, I mean, bad thing is still reactivity, even though the bright state fraction is pretty small. So And then the more atoms we have in the bright state, the more losses we have. And you can see here, this is the number of ion counts as a function of time. And then the data is fitted with a rate equation model, which is just slightly more complicated than we have it when we have a continuous density, because the ion atom overlap changes with time. The mod is loading, the ion cloud is also changing. But this we can measure independently, this overlap of the ions and atoms, and then we can fit out the reaction rate coefficient here in the exponential decay of the ions, which is not exactly exponential because, as I said, this is dependent here. And there's a tiny loss that has to be included, but it's actually, as you can see here, the background loss is actually very small. So with this, we can now plot the rate for this reaction process here as a function of excited state fraction. You can see here it follows fairly well a linear dependence from 0.1 to 0.3. I mean, that's sort of it was the maximum we reached here. And from the slope, including this error budget, we can then get the rate coefficients out either for a zero bright state fraction, that's the ground state reactivity, which unfortunately is not zero in this case, and for the excited state fraction, which is about a factor of 2.5 larger for the bright states, for the 5p states. Question is, can we understand this? And we did actually quite a bit of modeling thanks to collaboration with Milaim Kaas. And this shows us sort of the summary of all of it. Yeah? So first of all, let me see, it's a full slide. Here we have the potential of the interaction potential of the rubidium coming towards the OH as a function of the distance RB, which is plotted here. So you can see the attractive interaction down here for ground state rubidium, and you can see also attractive interaction here for excited rubidium. And what happens is when the incoming potential crosses over to a potential that correlates to the neutral, say for example this gray potential here, then the electron can be released. And so beyond these crossing points here in this case, and also here, is where you can go to the detachment continuum. This is unfortunately not easy to describe theoretically because you have this free electron and you go through, let's say, an infinite series of electronic wave functions. And that's why one has to resort to models and to calculate this more quantitatively. But that's sort of what's shown here in the picture. What you can see also here is the curve crossing for ground state rubidium actually lies up here at 2.5 electron volts. So that tells you that actually the reaction is forbidden. At least it's forbidden at this geometry, which is an 80-degree angle between the incoming RB and the OH bond distance. When we change the angle, this will change. But let's look first at sort of in comparison with what's easily calculatable, and that's the Langevin rate, which has been mentioned several times before. So the capture range rate coefficient when only the long-range interaction matters. And in this case, you have a substantial rate because rubidium is so polarizable that it's 4.3 in this 10 to minus 9 units. And for the excited state, which is even more polarizable, it's even larger. Both rates are, in a way, upper limits, and the experiments stay below that. But then, in order to figure out how much lower, one has to look at what happens at short range. And I show you here, there are curve crossings all along. And only for a very small range of angles for the excited state, there is no curve crossing. So essentially, together also with the different interaction potential, the theoretical modeling gives us a, looking a bit more closer, gives us a rate that is similar to Langevin, quite a bit larger than the experimental value. Whereas for the ground state, there are only very few angles that allow this process to happen. And when you integrate over these angles as a sort of fractional solid angle of the total, then the calculation drops from Langevin by a factor of 10 and even is a bit smaller than the experiment. This factor of 2, maybe that's anyway within the accuracy of the quality of these models. But that's where we are. You can see we understand qualitatively from this that we actually have a much lower rate for the ground state, even though the reduction in the excited state is larger than we would have guessed from this, and we don't still know yet what's going on in the excited state. And this can also be sort of viewed more pictorially. This is now the detachment just for the ground state of rubidium, which starts here, and where you see two different angles again. The 80 degrees I showed you before, where there is a 2.5 eV barrier to overcome, so this reaction will not happen at any low temperature. And at 0 degree, where this barrier is essentially 0, and you can go through an intermediate well here in both cases to get out into the neutral plus a free electron here. And what we found then is that, in fact, in this transient process here, there is an enormously large electron wave function involved, which represents a dipole-bound electron, which is a universal behavior of an electron bound to a dipole without any short-range interaction. In fact, in this reaction here, this dipole-bound state is transiently populated before the electron leaves. And you can see up here, only angles lower than 20 degrees are actually relevant. So it's a very small cone of acceptance in a way that has to be reached for detachment of the neutrals. Nevertheless, it still reacts substantially. Okay, so we know now how to control the population. We know the rate, and we're wondering if we could still see cooling in these collisions with rubidium. In a way, you can say we were persistent after working on this for many years. First of all, we have to understand the time of flight distribution to get out a temperature, because I showed you we can get temperature from density distributions, but it's more convenient, and Sadiq's shown this already many years ago, it's more convenient to get this from a direct time of flight distribution, because the width of the ion arrival time will depend on the width of the velocities in the ion trap. And this is a simulation of this mapping of the time of flight variance onto temperature. And measuring this, we can get out the temperature. And this actually, you see a curve here. This actually can be confirmed also with our density distributions in the trap. So it all makes sense. And it also scales qualitatively linear, but there are some deviations at low temperature that we can take into account. And with this, we did translational cooling now of OH minus, and you can see the temperature here measured in this way, which actually decreases, just doesn't decrease very much, down to 200, below 200 Kelvin in this case. And it depends on the position of the atom cloud with respect to the ions. At the same time, we also have losses, as you can see here, the number of ions because of this reaction rate. So we actually lose a lot of ions while cooling. And what we even more so realized is that we cool the best when the ion cloud is actually outside at the edge of the trap, right, of the ion cloud, at large interatom separations, whereas when it's at small interatom separations, it actually doesn't cool very well. And so what happens here is that we're actually not really cooling by elastic collisions, but we're removing the hot part. So we're doing kind of an evaporative cooling process using this species. And I don't have much time. I can talk about this later, but I have a few slides, maybe just one slide on O minus, because we also compared this to O minus atomic oxygen. And in atomic oxygen, we measured there is actually no appreciable rate at ground state rubidium. So we can do the cooling. And yes, we can do the cooling. And I show this here. From the initial temperature, we get a significant cooling in a few seconds interaction time, down to, say, I think 30 Kelvin or so, roundabout, when we, and in particular, it works best in this case when the atom-ion separation is minimal. So here, we can really put this on top of the ion cloud, and then we get the proper cooling, which is what we would expect from regular, cooling by elastic buffer gas type collisions. And then thinking about this, we realized that, well, if we can cool OH minus by removing the hot ions, then, well, we don't need a mod for that. We take our laser detachment beam for that, and we can do photodetachment-driven ion cooling. And this actually works like a charm, and we can do it forced, really moving like you can sort of, or people did many years ago, starting many years ago in Bose condensates, really driving the laser frequency into the ion cloud at the appropriate speed. And you can see here on a log scale, you can see here a drastic decrease in temperature, which depends on position, which in this case on the moving speed. And also we still have, of course, a loss of ions, but we can also show that there is a strong increase in phase space in this case. So we really talk about an evaporative cooling process in this case. And the lowest temperature we could see here was actually 2 Kelvin. So, with a maybe, given error budget, we're sort of on the edge of beating the helium limit with this process for, in this case, OH minus, so really for a molecular ion. And I should say that this is actually something that was predicted by Anne Crubelier 30 years ago, purely theoretically, and it works really very, very well. And so my time is up. Chairman is standing up. I flash one slide, and we can talk about this over dinner, because C2 minus is something we're now working on. It's a new project, and C2 minus is one of the very few negative ions that possess electronic excited states, and can be used and has been proposed to be used as a laser coolable ion. Well, that's for the future. We've done the high resolution spectroscopy of this now, but as I said, I will not talk about this. I'll say thank you to all the people who are involved, in particular Matthias Weidemüller and his entire team, and Markus Nötzold, the graduate student in my group, who's done a lot on this work, on all this work. And I thank you for your attention.
Thank you very much, Roland, for sharing these interesting results. Questions? Roland. Carlos.
Actually, like going back to the last slide you haven't shown, like what are the lasers for cooling this C2 minus?
Yeah. So this is a the green transition V equals 0 to 0 is 541 nanometers. Yeah. So we're using a frequency doubled diode laser system for this.
Possible cooling. There is any like close or almost close like cooling transition that you can get like there, or it's?
So yeah, so it's not closed, unfortunately, because it's a molecule, but you can see the Frank-Condon factors here. 70% of the excited state will decay back to the ground vibrational state, but 30% will go into higher excited vibrational states. And all of this has to be repumped. And then, of course, there's also rotational states. So we drive the transition from J equals 0 to J equals, or let's say N equals 0 to N equals 1, which will decay back to N equals 0 and N equals 2. And so on. So there are, in the end, if you want to laser cool this, you'll need a dozen lasers or something like this. And they have frequencies from 500 to 700 nanometers. Yeah? So depending on what, that's why, yeah, this is a long road. Yeah? But it's better than almost any, or probably any other negative ion that is known. Yeah?
Further questions? Johannes.
So can you perhaps go back to this dipole bound electronic state? I don't know, I didn't pay much attention there, but there was kind of with this kind of Rydberg big orbital, or what is this? Yeah, so yeah. Can you explain a little bit more what we're talking about here?
So an electron can actually be bound to a dipole. So if you have a point dipole, and this has been actually shown for the first time in the 1950s or 60s, then you can find bound states, bound state wave functions, if the dipole is larger than a critical value, about 1.7 dBi. And in this case, you don't need any like short-range interaction. It's just the point dipole and the interaction field that this creates on an electron. And that leads to a very delocalized electron wave function like this, much, much larger than the size of atoms or molecules. And that's the case that what we have here, that the shape of the wave function of the excess electron in the vicinity of this RBOH, which is also a very dipolar system. This is, no, these are not ground states. This is, well, actually, no, in this case, it would be even the ground state. Yeah. Mm-hmm. No. But these are typically bound by fractions of millielectron volts below the detachment threshold. So they're very weakly bound. And there is, in fact, you mentioned Rydberg, there is sort of a series. It becomes a bit more complicated once one includes rotations of the molecule, but there are typically more than one. Yeah? There's a series of states.
Further questions? If not, then okay, maybe we can carry this on later. Let's move on in the interest of time. Our next speaker will be, so first let's thank Roland again